University of Crete, Marina and Bitsaki. And she will present a paper about optimization, and it's about collective utility in hierarchical structures of collective adaptive systems and application in transportation systems.
Okay, good afternoon. My talk is about decision making in collective adaptive systems. And this work was done in the context of the SummerSOC project, in which, among others, we have studied about design principles and models of large-scale collective systems to accomplish goals with high quality in dynamic environments. So a collective adaptive system consists of heterogeneous entities that collaborate and interact with each other in order to accomplish individual goals and overall collective goals. They consist of the main components of such systems are the entities that take part and collaborate with each other, the cells that encapsulate the functionality of these entities and these entities offered to the system, and the ensembles, which is a set of all these entities and accompanied by their functionality, in order to fulfill an overall goal. An example of such a collective system is an urban mobility system that offers transportation services to passengers. Entities of such systems may be the passengers, the drivers, the companies that own the transportation services, their managers, the route managers, or multiple route managers. And an example of an ensemble might be a specific route that transports people from one point to another. Now, what are our main contributions in this paper? First of all, we have introduced the concept of collective utility of the ensemble. Then we have proposed a hierarchical model in order to calculate this utility in steps, and you will see that this model has advantages. First of all, it facilitates computations, and second, it is very suitable in environments of incomplete information that is shared among the entities, and these advantages will be recognized after we have presented this model. And third, we have applied these concepts and models in the urban mobility system, and we have seen how we can make decisions, optimal decisions, through maximization problems. Okay. Now, first of all, the utility, which is a very well-known notion of an entity, is a way to measure the satisfaction this entity experiences by using a service. Okay. Now, the collective utility of an ensemble, which is not such a common concept, is a way to measure the overall welfare of all participants of this ensemble, of all entities of this ensemble. We have given the following formula in order to define, to calculate this collective utility of, for example, ensemble E, which takes as input, first of all, the vector A, which is the parameters of the utility function, In our example, in the air mobility system, such parameters may be the travel time, the cost of the trip, the waiting time, the walking distance to the bus stop, the comfort in the bus, and many others. Also, an input to this collective utility is a vector of this WI, the vector of the entity's preferences, because the entities have preferences. For example, in our transportation example, a passenger might have a constraint on time, might have an upper bound of cost, and others. And also, and then if we have the input, we can aggregate all, in order to calculate the collective utility, we can aggregate all utilities of the various entities that are part of this sample in given weights. These FI functions are weights that show the importance of each entity in contributing to this total, say, utility. This is a very general definition. Later on, I'm going to give you some more specific example on these parameters and values. Okay, so why is this collective utility important? First of all, because we have found a way to evaluate the samples. Because we need to make decisions many times in systems which ensembles to create, which ensembles are not good enough, and discard them, and so on. Second, with this collective utility, we can make collective decisions for groups of people. And third, we can improve the performance of service systems. Later on, we are going to see some examples of that. So, okay, now we have the concept of a collective utility, but how can we need much information from different actors, from different entities, and in different levels in order to calculate it. So here, we provide a hierarchical structure in order to calculate this collective utility. First of all, let's discuss about the hierarchy of ensembles, because when we have complex systems, we might have complex ensembles that consist of other ensembles, and these ensembles may consist of other ensembles, and so on. So we have a hierarchical structure, and in parallel to this, we construct a hierarchy of the utilities of these ensembles. Here in the figure, we have an example of a very simple example of the two-layer hierarchy. Here, in the transportation system, this might be a route with a bus, and this might be a route with another bus, or any routes of different itineraries, right? And each one of these is an ensemble, and all of these are coordinated by the company who owns the buses. And we have the ensemble here, which consists of all ensembles and all their participants. Okay, now, in order to calculate this utility, the collective utility of the big ensemble there, we first need to calculate the collective utility of each one of the ensembles here by using an aggregation function GI, for example. It might be anything here. And then use these utilities, aggregate them again, and compute the overall utility. What is very interesting and difficult in this procedure is to determine these aggregation functions. And a factor that plays an important role for determining such functions is to recognize that there exist complementarities and interdependencies among the entities that belong to the different ensembles. Here, we have identified 3 different cases. These are 3 different examples, let's say. The first case, we allow entities to belong in more than one ensemble in the lower level. So one entity might belong in a one route and in the second route, for example. Another case is when each entity belongs only to one ensemble in the lower level, And the third case is that all entities are part of all ensembles in the lower level. Next, we give examples for the three cases and how we calculate the collective utility in the case of a transportation system. So let's describe this scenario. Consider we are interested in offering transportation services in a smart way in the city, where we have passengers with the objectives, with preferences. We have also transportation means buses, taxis, carpooling, flexi-buses. Flexi-buses are something between buses and taxis. And we have fixed routes, or we have dynamic routes. We don't know the pickup points at hand, but on demand, based on bookings, for example. We also, in this complex system, we have environmental changes, so we might face delays. Something might go wrong in the road, accidents, and so on. So we need a system so that in order to manage and coordinate all these different aspects and provide finally services to citizens. Okay, so our scenario consists of some entities. The entities are the passengers, of course, the bus drivers, the route manager who coordinates all the actions of a single specific route, and the flexible manager who coordinates a number of different routes that might interact. For example, these might be consecutive routes for passengers that want to go from one point to another and then from another to another for their final destination. So, in this scenario, we have a first example, and the first case is the case where we have two routes, a route from A to B, a route from B to C, and we have passengers that are interested in these two routes, but we have also passengers that are interested to go from A to C, called the path passengers. Okay, so here we have the first ensemble, which is route 1, the second ensemble, which is route 2. Here, some of the passengers in red are interested in both, as you see here, in both buses routes. And here is a way to define the utilities. The first one, UI, is the utility. This is a decreasing utility time, and exponential, and is the utility of the passengers when travel time is T, when their maximum travel time is W. They don't want to go over this time. And where K is one of their preferences, it's the risk tolerance of the passenger, which means that the higher the delay, the higher the decrease in utility. If this happens, then this is a risky passenger. This is again a preference of passenger that specifies the type. Next, this is the collective utility of the whole route of the first route, which is a weighted sum of the utilities of the passengers in this route, where WI are the preferences of the passengers, the maximum travel times of the passengers. So here we give more weight to those passengers that are willing to have higher delays. Okay, this is just an example. Then again the same, we have the collective utility of the second ensemble, the second route, and then we have a weighted sum in order to calculate the whole system's collective utility, and these weights correspond to take into consideration the number of participants in each specific single ensemble here. So the higher the number, in an ensemble, the higher the weight, the more he contributes to the overall utility. Okay, now, of course here we exclude the number of common, the number of the common passengers. So we don't have to take them twice in the calculation. Now, a second example is the following scenario. We have we have to pick up from different origins, various passengers that all have the same destination. For example, they all want to attend a concert or anything else. Now, this city planner has to organize what is the transportation mode that will be chosen for each of the passengers. They can choose a flex bus or they can choose a taxi. We have again references for them about the maximum travel time and about what each passenger prefers most, taxi or flex bus. We have taken these into account too. And then here is an example of the utility of the passenger. Okay, and here is the weighted sums in order to calculate the collective utilities of these two, of the flex bus, of this example, and this is on the taxi. And then here again we aggregate these two in order to calculate the overall utility. And a completely different example here, which is the third case where all passengers in this level are the same. These are the same passengers as these ones. And the scenario says that, okay, the passengers all belong to a route that is being executed, and at some point there is a failure. So the bus must stop, and the route manager, the flexibus manager, the company manager has to find another, not only one, maybe more alternatives. So he finds here in example two alternatives. The new route is R1, and the second new route is R2. Then we have to decide which of the two routes to choose. And the criteria here is the one that increases the total welfare, that is the collective utility. And the collective utility says here, the collective utility of the whole system is the maximum of the two. Okay. Now we use this first example. Let me remind you, this is an example where we have two routes from A to B and B to C, and we have also path passengers. So here we want to see how decision making is performed, because till now we have only seen how to define utilities, collective utilities, and so on in a hierarchical way. But we have not discussed this decision-making thing. So we will do it in the first scenario. And we consider that we have requests from A to B, we have requests from B to C, we have requests from A to C, path requests, and the requests are more than the capacity of the buses. So the decision the manager has to make is what is the allocation of passengers to the seats, to the buses. So that the criteria again is the collective utility is maximized. So the maximization problem we need to solve is to maximize the collective utility of a set of the subset of the passengers of the requests, such that all capacity constraints on the buses are satisfied, and at the same time the constraints imposed by the passengers are also satisfied. For example, the travel times are less than my maximum travel time, right? So, what is our approach now? One way to solve it is use maximization theory and taking all different combinations, which is very time-consuming, and the computations are the number of computations is large, and also the information needed is not known by for example, by the company manager who needs to solve it, right? So we overcome this difficulties with our hierarchical approach. Too much information here, okay, I'll try just to describe it in a few words. First of all, our assumption is that the FlexiPass manager in the top level of the hierarchy just sends path requests to the different route managers of the two routes, for example. Then each route manager just computes the optimal allocation only to his own bus, and this is done by both separately. And then they combine again their allocations, and there is a danger here. What is the danger? That one path passenger that might be accepted in first route might not be accepted in the second route, since they are done separately. So the FlexiPass manager takes this list of path passengers and rejects all of them, all of the path passengers that did not win both leagues. And the available then seats are filled by the next best single route passengers. This is our way of solving this problem. We have run experiments on this. These are some route characteristics randomly generated. Also the passenger profiles here. We have 3 types according to their preferences. These are uniform distributions with these ranges. Okay, and we have run various experiments, and we have used these utility functions. Again, we have already seen the first one. This is the utility of each passenger, depending on travel time, on their type, and on their preferences on travel time. Here we have the utility of the first route, which is the weighted sum of all passengers utilities, weighted, and this W denotes the weight given to path passengers, which means that if this W is high, we give more priority to this path passengers. Again, U2 is the collective utility of the second route from B to C, and U is the collective utility of both routes of the whole system. And using these functions, we run our experiment. We run our experiments 100 times for different values of W, and here are our results. First of all, using W as 1.1, we calculated the optimal. The optimal one, and compared it with our hierarchical, the red line is our approach, the blue one is the optimal, and we see that we're very close to the optimal one. Here we have the value of collective utility in this axis, and here we have the number of runs. We have how many runs. Okay, this fluctuation is because we have random input. The second type of experiments shows that if we increase this W, which is the weight to give priority to path passengers, this error were even closer to the optimum, the maximum value of collective utility. And if we increase a little bit more the weight to 1.3, we have exactly the optimal, our solution gives the optimal value of utility. And any number above this, again, has this graph. And I think we've finished now. We have, so in order to sum up, we have defined the collective utility in the way hierarchically calculated, and the success of this approach depends first on how we define the utilities, so that all the preferences are well understood through these functions, and second, how well the different levels coordinate and share information in order to and the knowledge in order to make the aggregation in a very scalable way. Thank you.
around for questions.
Have you considered approaches from game theory, like Nash equilibrium, in comparison to your approach?
Not in this. I have done this. We have used game theory in other settings, in other examples when we have to answer other decision problems, but not in this way.
Other questions? I have one about the, you have experimental results. You have done some experimental results. Was it on this real map of transportation you showed at the beginning? It was from North and Italy?
No, the data were just inverted by us and used randomly, randomly ranges chosen that are logical, but not from real data. No.
Any further question? So it's not the case. Thank you very much.
So before we leave, we are now going to the coffee will be served down at the restaurant called Fontana Amorosa. Fontana Amorosa. Who does not know where it is? You follow me. Yeah? Okay? Follow me. We are going to Amorosa.
On your head, and on your shoulder.
And then, so at 5 we will start then with the poster sessions, and I hope that everybody will be there. And I recognize that some